All right, so after today, you should be able to describe the different parts of the atom. And if I give you a nuclear symbol, can you tell me how many protons, electrons, and neutrons are found in that particular atom? We'll see. We'll see. All right, the periodic table showed us that some elements had similar properties. But what did it not answer? What does the periodic table not answer for us? Hank Green said this rather emphatically. He asked, why? Why do they act the way they do? Why? Well, as we'll find out, it has to do not with the number of protons, but the number of electrons. And that's what we're going to focus in on in this chapter. So, what are all atoms composed of? Middle schoolers. Protons, neutrons, and electrons. Where the protons are positive and the electrons are negative, and the neutrons are neither. That's why they're called neutrons, because they are neutral. All right, so it's hard to understand exactly what an atom looks like, so here is a metaphor to help you. The great state of Tennessee.
Wow, good job.
That's Memphis. Over here is Knoxville. And in Knoxville, you're going to find Neyland Stadium. In Neyland Stadium, there's a field with a big fat T on it. Imagine on that T, for the atom sodium, you will find 11 large watermelons and 12 large pumpkins. The watermelons represent the protons. The pumpkins represent the neutrons. That right there, in a neat pile in the middle of the power T, is the nucleus of the sodium atom. Now, where are the electrons? First of all, what is an electron? An electron is a tiny little gnat. A gnat, folks. You know those little teeny tiny flies that drive you crazy, which are too small to swat. And they and you can hear them around the ear. If they get around my ear, they drive me crazy. Stop! Okay, that is an electron. As compared to a watermelon. Watermelon, electron. Okay, where will you find the first electron? You'll find the first electron on the topmost seat. I mean, we're talking nosebleed section, as far away from that power T as you can possibly get. That is your first of 11 electrons for sodium. Then you will find the final electron. In Memphis. The 11th electron in Memphis. So between there and Memphis are 9 other electrons. So as you travel the great state of Tennessee and Alabama and Georgia and Kentucky and South and North Carolina and Virginia, what are the chances you're going to encounter an electron? That's the size of a gnat. Very, very small chance. But they're there. They're there. So what is most of what an atom is empty space.
Whoa.
Empty space. Let's see what Hank Green has to say.
All the stuff that we think of as stuff is made of atoms, tiny, discrete particles that have specific properties depending on the arrangement of 3 simple subatomic particles. There's the proton, heavy and positively charged, the neutron, about the same size as the proton but neutral, and the electron, which has the same amount of charge as the proton, just opposite, and very nearly has no mass at all, about 1,800 times less massive than the proton or neutron. Protons and neutrons hang out in the nucleus, and thus are the nuclear components, or nucleons. Electrons hang out around the nucleus and are the parts of the atom that do all the interesting chemical stuff. But before we get to the chemistry of the electrons, we first have got to understand the properties of the nucleus. Okay, this is pretty important, so pay attention here. The number of protons in an atom determines what element it is. 79 protons, always gold. 59 protons, always praseodymium. The number of protons in an element is its atomic number. It sits right on top of the box in the periodic table because that is the element's defining trait. So an atom of silver with 47 protons in its nucleus is always an atom of silver. Depending on what its electrons are doing and what it's bonded to, it might be part of a chemical that's silver-colored or black or blue or shiny or poisonous or a cure for disease. But whatever it is, that atom is still silver and will remain an atom of silver probably forever, because that core number is very, very difficult to change. Nuclei, which is the plural of nucleus, are boring. They're thousands of times smaller than the atom as a whole, and they mostly just sit around being exactly the same as they were when they were first created billions of years ago, held together by the strongest of the four fundamental forces of physics, the strong nuclear force. In fact, the nuclei are so boring that the very reason they're the defining characteristic of elements. While electrons can jump from atom to atom whenever it's convenient, the number of protons is almost always extremely stable. So that core of the atom, the nucleus, always comes out of chemical reactions unscathed. It's the bit that we can bump around from reaction to reaction, but always remains pure and behaves the same way as any other atom with that number of protons. The atomic number is the soul of the atom. It's what makes it. Neutrons are important too, of course, in their own way, but they don't change what element an atom is. One of the two keys to all things chemical is charge. We'll discuss that in another episode. And since neutrons don't have any charge, they mostly don't change the properties of an atom. But they are nonetheless vital. We all know that like charges repel each other. Neutrons serve as a kind of buffer between the protons. You couldn't pack silver's 47 protons together in a nucleus by themselves. They couldn't handle it. They'd rip themselves apart. So nuclei only clump together permanently when the right number of protons and neutrons get together. Silver needs about 60 neutrons to space out the 47 protons correctly. But it doesn't have to be 60. In fact, silver nuclei are also very stable with 62 neutrons. 61, though, that doesn't work. And the reasons for that, I don't know. You would have to talk to a nuclear physicist. The atomic number of silver doesn't change as the number of neutrons changes because the number of protons stays the same. But the relative atomic mass does change. Relative atomic...
Okay, we'll end right there. So, basically what did he say? He said that the proton is found in the nucleus along with the neutrons. So protons and neutrons are nucleus inhabitants. They are roughly the same size, so we say that they have a mass or a size of 1 U. The U stands for atomic mass unit. Folks, their mass in grams is so small, it's to the negative 24th. So the number is so little that it boggles the mind how little it is. So we have come up with a brand new mass unit for measuring bits of atom. And that mass unit is called atomic mass units, or U for short. So the smallest particle, the proton, has a mass of 1 unit, the smallest nuclear particle. There are electrons, and electrons are tiny even compared to a proton. They're 1,840th the size of a proton. So roughly for you and me to understand, if a proton is a watermelon, an electron is a gnat. A gnat, right? You probably call them gnats, but there's a G there, gnat. Okay, what is the Social Security number of all elements? What is the only number that you can use to distinguish one element from another? The number of protons. The number of protons. It is the ID number of an element. Another name for the number of protons is the atomic number. The atomic number, which has a symbol of Z. That's why I don't call it the atomic number. I call it the atomic number, to remind me that its symbol is Z for number, not for zero. Where can you find the atomic number on the periodic table? Look on your periodic table, since your periodic table should be out. Where do you find the atomic number? No. Where is it? No, that's the mass number.
Where is it at?
It is the number that is on top. The atomic number is the whole number that is on top. of the symbol. The whole number that is on top of the symbol. So, knowing that, Emily, what is the atomic number for sodium?
Give me a second. Where is that?
Sodium is a metal, my dear.
Oh, yeah. Oh, it's 11.
11. Roche. How about fluorine? Very good. Devon, magnesium. Very good. Rone.
Really?
I'm sorry. Gracie. Hydrogen. 1. Asher. Titanium. What? 22. How is the modern periodic table arranged? Did you notice? Go from left to right. What happens to atomic number? It increases. It is by increasing atomic mass. By increasing atomic mass. I'm sorry, increasing atomic number. Thank you. It used to be by increasing atomic mass, but Mendeleev ran into a lot of problems because of it. It is by increasing atomic number. Increasing atomic number. All right, so what aspect of atomic number really determines how an element will act? Well, actually, the atomic number not only gives you the number of protons, but in a neutral atom, it also gives you the number of electrons. It is the number of electrons, Isaac, that gives you personality, not the number of protons. So the number of protons is just, okay, that's Isaac. That's Isaac. But how Isaac is going to act will depend on the number of electrons it has. The number of electrons. So under normal circumstances, Ben, the number of protons equals the number of electrons. Getting all this? Excellent. So what do we call the sum of protons and neutrons? If we were to take the number of protons and neutrons and squish them together, we would refer to it as the mass number. The mass number. The mass number is protons plus neutrons. Protons plus neutrons. Now you're probably wondering, well, what's the number down on the bottom? We'll get to it here in a second. Okay? Chill. So what is the relationship between the number of electrons and protons? Well, in a neutral atom, the number of protons and electrons are the same. In a neutral atom, the number of protons and electrons are the same. So if you have 11 protons, you have 11 electrons. So, what symbol do we use to describe atoms, to be able to tell how many protons and neutrons atoms have, or even how many electrons? We use nuclear symbols. Nuclear, or as President Bush used to say, nuclear. 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 Nuclear symbols, or nuclear symbols. What is a nuclear symbol, or a nuclear symbol? A symbol that includes the mass number. So the mass number is on the upper left as a superscript. The atomic number is on the lower right as a subscript, and then the charge, or just 0, is on the right. Spencer, nothing on the bottom right. Nothing goes there. All right, let me give you an example of a cation. What's a cation again? Positive ion. All right, sodium 24, 11 plus 1. That would be a nuclear symbol for a cation. An anion, what's an anion again? Sulfur 32, 16 minus 2. And then, of course, if you have a simple old neutral atom, it would be something like this. 16. If you see a 0, then what that means is however many number of protons you have, that's how many electrons you have.
What's the O? Is that neutral?
Neutral, yes. That means nobody's winning. So, if you look on the periodic table, you're going to find something very interesting. The number below the symbol is its mass number, but it actually has decimals. Why does it have a decimal? Well, have you heard of identical twins?
Yes.
Okay. Every element has an identical twin which is slightly different from it. Its mass is slightly different. So what you're seeing there, with it being a decimal, what you're seeing is the average of all of the siblings of each kind of element. It's not just an average, it's a weighted average, which we'll talk about it eventually. But for now, those numbers that are below the symbols are not true mass numbers. They are the average of all the mass numbers of all the different siblings of any particular element. What do we call the siblings? Isotopes. These are atoms that are basically the same thing. They're all sulfur, they're all oxygen, they're all carbon because they all have the same number of protons, but they have different numbers of neutrons. Different numbers of neutrons. They're kind of like identical twins. Who are they? Not John and James. No. John and James are fraternal. What? The Goldmeyer twins. Oh, Esther. Oh, I haven't met her twin. I need to meet her twin. Okay, so the Goldmeyer twins are isotopes. They're slightly different. If you were to look at their DNA would be 99.999999999% the same. And there's a tiny little difference. We can say that they are isotopes of each other. Okay? Isotopes of each other. Different flavors of the same element. Same number of protons. Different number of neutrons. So they're going to differ by the number of neutrons. They're going to differ by the number of neutrons. Let me give you a couple of examples which are very important to us. You ready, Ben?
Yep.
All right. Uranium 238 92 and uranium 235 92. They're both uranium, but one uranium has 3 less neutrons. 3 less neutrons. How many neutrons? Let's see. 3, 4, 143 neutrons there. Because remember, this number is the number of protons and neutrons. Protons and neutrons. So if you want to know the number of neutrons, you need to subtract. Okay, so during the war, that was good uranium. That was the uranium that we could make into a bomb. This was bad uranium. That uranium was useless to us. So Oak Ridge was created in order to take a ton of uranium, raw uranium, containing uranium-238 and 235, in hopes of getting about a pound of uranium-235 out of it. The vast majority of all the uranium in the world is 238. Useless. So the hard part in making a bomb is getting rid of as much of the 238 as possible in order to have just mostly uranium-235. And it's actually not even mostly. You just need to get it up to 15%. Normally, it's about 99.2% this and about 0.8% that. If you can get that percentage up to 15%, baby, you can have a nuclear bomb. So, the whole reason why we're sitting here in Oak Ridge, Tennessee, was we had to differentiate. We had to enrich the uranium. And what's the difference between them? 3 neutrons. That's it. That's all they had to work with. They somehow had to separate two things that differed by 3 neutrons. I'll explain to you how they did it later. Here's another one. One of these days, even Ben Walls is going to die. He has a certain amount of radioactive carbon in his body. Most of it is carbon-12, a little bit of it is carbon-14. When he dies, eventually that carbon-14 breaks down into non-radioactive nitrogen, and we can actually be able to tell how old his body is by measuring how much carbon-14 is. We're talking a difference of 2 neutrons. That's it. Two neutrons. That's it. All right. Your chart is wrong. Make sure you fix it. I think the first one is correct, but the other two have the wrong numbers on them.
Oh, I got the good.
All right. I need to explain to you how, if I give you a nuclear symbol, how to be able to figure out the number of protons, electrons, and neutrons. And you know who's the perfect person for explaining this? Gracie.
What?
Gracie. Thank you, Gracie, for volunteering. Okay, now, let's review, Gracie. This is the number of protons plus neutrons. Oops. This is the number of protons. Why is it doing that? Okay, so how many protons does sodium have? That is the number of protons and neutrons. Okay, let's review. This number is the number of protons and neutrons, which has the neutrons part, which we don't want. Okay, this is the number of protons.
Oh.
So how many protons does it have?
Sorry,
11. All right. How many neutrons does it have? You were on the right track.
Yeah, so 13.
13. My tablet has gone back to touch screen, and every time I touch it now it does that. All right, I don't know why it does it. In the middle of me using it, all of a sudden it wants to be a touch screen again. Okay, so we'll have to be patient. All right, so Gracie, here's your clue for the number of electrons. It's just a clue. What number is right there? There's no number there. So the number is nothing or 0. So who is winning the battle between protons and electrons? Okay, if 0 is the score, who's winning the battle between the protons and electrons?
Wait, what?
The score should be right here. Gracie, the score is right there. What is the score? 0. So who's winning the battle between protons and electrons? What? Nobody is winning the battle. If the score is 0 on Friday, 0 to 0, who's winning the game?
Okay.
Nobody is. So that means that in the eternal battle between positives and negatives, protons and electrons, no one is winning. So if you have 11 protons, how many electrons must you have if no one's winning the battle?
Okay.
How many? What?
Like none.
Okay. If that was the case, then the protons would be 11 and the electrons would be nothing. So it'd be a charge of positive 11. This doesn't tell you the number of electrons. It tells you who's winning the battle. So who's winning the battle if you have 11 protons? How many electrons do you have if no one's winning the battle? 11. That's right. Okay, poor Gracie was our guinea pig.
Is it negative 11?
No, it's just 11. Okay, the protons are negative 11. No, the protons are positive 11. You can think of the electrons as being negative 11. So who's winning the battle if you have 11 positives and 11 negatives?
Nobody.
Nobody. So if the charge is not there, That means the charge is 0. If the charge is 0, however many protons you have, that's how many electrons you have. The same number. But if the charge is positive or negative, that tells you something. Something very important. Riker! Iodine. Notice there's no number right there. That's because they don't have to tell you the number. Okay? They don't have to tell you the number, because if you can find iodine on the periodic table, you found the number. So what is that number? So the number of protons is 53. Okay. How do you find the number of neutrons, Riker?
126 minus 53.
Yes. What is it? 126 minus 53.
73.
Riker, there should be two things on your desk. There should be a periodic table and a calculator. Okay. So, does everyone understand that? In order to find the number of neutrons, you have to subtract the mass number from the atomic number. These two numbers have to be subtracted.
So, what's supposed to be?
53.
How did you get?
Periodic table. Iodine is number 53. Number 53 is iodine. Okay, Riker. Who's winning the battle? Who's winning the game? -1 is your charge. Who's winning the game? The positives or the negatives?
Hey,
Well, if it's -1, I don't think so. Try again. The electrons are winning by how many? Okay, so how many protons do you have? How many electrons must you have if the negatives are winning by 1? Yes. See how easy that is, folks? Who's winning the battle? The negatives. By how much? By 1. So if the negatives are winning the battle, how many negatives do you have? Well, how many positives do you have? 53. If the negatives are winning by 1, then you must have 54 negatives. Yes,
It
Serenity.
says on iodine. At the
Serenity, I said these numbers were messed up.
Okay, good. So I'm so confused.
Randy, keeping in mind that the number on your piece of paper is messed up, it should be 88. Strontium. How many protons? He's looking for it on the periodic table because they did not give it to him. Do they have to give it to him? No, they don't have to give it to him. Because if he can look it up on strontium, he knows what it is. What is it? 2. The number 2. So strontium's atomic number is 2.
I believe that's helium.
That's helium, my friend.
My friend.
What is 38? 38. Good save there, Randy. All right, Randy, since you know the number of protons and neutrons is 88, and you know the number of protons is 38, how many neutrons do you have?
50.
And how did you determine that? 88 minus 38 is 50. Good. All right. Where's your clue as to who's winning the battle? Who's winning the battle between the positives and negatives? Positives by how many? So how many positives do you have? That's helium, my friend. How many positives do you have?
Oh my god.
How many positives do you have, Randy? 38. If the positives are beating the negatives by 2, how many negatives must you have?
36.
Don't say 2, please. Do not say 2.
I'm really needing that.
2 is not going to be the answer for any of these. If the positives are beating the negatives by 2, and you have 38 positives, how many negatives do you have?
32.
Oh, we got it.
Well, he had some help.
Actually, nobody told me that.
Okay, good. Good. All right, gang, do you see that? Do you see how easy that is? This tells you who's winning the battle and by how many. And then all you have to do is focus on the protons. If the protons are winning, you have more protons. So how many electrons? You're going to have less electrons. If it's plus 3, you have 3 less electrons. If it's minus 2, then the electrons are winning. So you're going to have more electrons. All right, Jeffrey. This thing has 33 protons. What is it?
Arsenic.
He looked on the periodic table, and behold, arsenic was number 33. Do you see that? Okay, so now you are already halfway done. You need the top number and you need the charge. All right. Jeffrey, what is its mass number?
73.
Whoa! How did he do that? He added those two numbers together. The top number is the number of protons and protons and neutrons. All right, Jeffrey, what is its charge? 0. How do you know? Well, what's the difference between positives and negatives? Nothing. So if there is no difference, if no one is winning, then it has a 0 charge. Let's finish this real quick.
I got this one.
All right, iron, right?
Yeah,
26.
And then 57.
57.
And plus 3.
And plus 3. How about the last one?
Sulfur.
Sulfur, number 16. What's the top number?
2.
32. What is its charge?
Minus 2.
Okay. So I have
All right.
worksheets.